The power of neural networks comes from combining these units into larger networks. One of the most clever demonstrations of the need for multi-layer networks came from the proof by Minsky and Papert in 1969 that single computing units couldn't compute some very simple functions of their input. Consider the task of computing elementary logical functions of two inputs, like AND, OR, or XOR. As a reminder, here are the truth tables for those functions. So 0 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1, and so on. This example was first shown for the perceptron, which is a very simple neural unit that has a binary output and does not have a nonlinear activation function. The output y of a perceptron is 0 or 1 and is computed as follows. So using the same w, x, and b's that we've just seen, if w dot x plus b is less than or equal to 0, a perceptron will output a 0. And if w dot x plus b is greater than 0, it'll output a 1. It's very easy to build a perceptron that can compute the logical and or OR functions of its binary inputs. So here on the left, we have an example of logical AND. So we have weights, W1 is 1, W2 is 1, and we have a bias of -1. And logical OR has slightly different weights. This set of weights and biases are just one from an infinite number of possible sets and weights and biases that would implement these functions. Let's see what happens, for example, with the value 1 and 0. So if x1 is 1 and x2 is 0, then we have 1 times 1 here, 0 times 1 here. So we have 1 plus 0, that's w dot x, and then plus b, that's -1, and that equals 0. So sure enough, we get the correct answer 0 for AND. Now what about with 1 and 1? So we have x1 is 1, x2 is 1, so here we have 1 times 1, and here we have 1 times 1, and so we have 1 times 1 plus 1 times 1 -1, that's w dot x plus b, and so that's going to be 1. 1 plus 1 minus 1. Sure enough. How about OR? Let's see 0 and 1. We have a 0, we have a 1, so we have 0 times 1 plus 1 times 1 plus 0, and that's correctly going to give us 1. However, it's not possible to compute XOR with perceptrons. You should pause the lecture and try for yourself. Why isn't it possible? Crucially, the perceptron is a linear classifier. For a two-dimensional input, x1 and x2, the perceptron equation, w1x1 plus w2x2 plus b equals 0, is the equation of a line. And we can see this by putting it in the standard linear format, x2 equals minus w1 over w2 x1 plus minus b over w2. So here we have a slope. This line acts as a decision boundary in two-dimensional space. The output 0 is assigned to all inputs lying on one side of the line, and the output 1 to all input points lying on the other side of the line. If we had more than two inputs, the decision boundary becomes a hyperplane instead of a line, but the idea is the same, separating the space into two categories. Let's see a picture. These figures show the possible logical inputs, 0, 0, 0, 1, 1, 0, 1, 1, and the line drawn by one possible set of parameters for an AND and an OR classifier. Notice for XOR that there's simply no way to draw a line that separates the positive cases of XOR, 0, 1, and 1, 0, from the negative cases, 0, 0, and 1, 1. We say that XOR is not a linearly separable function. Of course, we could draw a boundary with a curve or some other function, but not a single line. Let's see an example of how to compute XOR using two layers of ReLU-based units. The middle layer, called H, has 2 units, and the output layer, called Y, has 1 unit. This set of weights and biases will compute XOR. Consider the input x equals 0, 0. If we multiply each input value by the appropriate weight, sum, and then add the bias, we get H1 will be ReLU of 0, dot 1, so our inputs are 0, plus 0 dot 1, that's this one, plus the bias, which is 0. So that will be 0. H2 will have value of 0 dot 1 plus 0 dot 1 for these two. But now minus the bias is a -1, so we'll get value of -1, which is 0. So we've got H as 0, 0, and then Y is 0 times 1 here, plus 0 times -2, plus 0 equals 0. I recommend you pause the video and work through the computation of the remaining possible input pairs to see that the resulting Y values are 1 for the inputs 0, 1, and 1, 0, but remain 0 for 0, 0, and 1, 1. It's also instructive to look at those intermediate results, the output of the two hidden nodes H1 and H2. Here's the original X space, where XOR of 0, 1 or 1, 0 should return 1. And now let's look at the values of the H layer for the same 4 inputs. Notice now that the hidden representation of the two input points, x equals 0, 1, and x equals 1, 0, those two cases where XOR output is 1, have been merged to a single point. The hidden value is going to be 1, 0 for both of those. This merger makes it easy to linearly separate the positive and negative cases of XOR. Here's a sample line that does that. In other words, we can view the hidden layer of the network as forming a useful representation of the input. In this example, we just stipulated the weights, but for real examples, the weights for neural networks are learned automatically using the backpropagation algorithm we'll turn to. And that means the hidden layers will learn to form useful representations. This intuition that neural networks can automatically learn useful representations of the input is one of their key advantages. We've shown why single units cannot compute XOR, and how multi-layer networks with nonlinearities are able to learn representations that make it possible to solve this problem.